All right, good afternoon, everyone. So thank you very much for this opportunity to get to talk. So we're going to fast forward a little bit in time, about 1.5 billion years, to the Devonian, and talk about the plant revolution, how the advent of roots impacted global biogeochemical cycling. Kind of an important point here, why the Devonian? Why is it so unique? So I would argue that it's fraught with tremendous biological, ecological, and atmospheric change. It hosted 3 pretty extraordinary events. The first being, as I mentioned, the expansion and radiation of land plants. So the advent of large root systems, trees, modern weathering, soil formation processes, and then modern nutrient cycling as well. So there's also evidence of eutrophication in Devonian oceans on a global scale. And then, of course, there's not one mass extinction in Devonian, there's 6. So it's a very dynamic time in Earth's history. So let's talk a little bit about the expansion and radiation of land plants. So the figure on your left, tiles A and B, show what the Devonian probably looked like kind of early in the period. So you have some land plants, but they're basically relegated to areas immediately adjacent bodies of water. You have no trees, and the root systems were very, very shallow. So you fast forward towards the middle, towards the end of the Devonian in tiles C and D, and you see a completely changed landscape. So you now see land plants basically inhabiting continental interiors. You see trees, and then if you look at the figure here on the right, you'll notice that as the Devonian progresses, the root systems also become fairly extensive as well. So we have large root systems, more soil formation, weathering, that sort of thing. So as I mentioned, we have 6 mass extinctions in the Devonian, some of which are much larger than others. We have the end Devonian mass extinction and the upper and lower Kalwasser events, fairly large. But what's important to note about all of these mass extinctions is that they're all characterized by one thing, and that's marine anoxia. Whether it's global or localized, they all have it. So there have been some authors who have tried to link these events together, and probably the most prominent of which has been a theory proposed by Algeo and Scheckler in 1998 that basically said that this rapid radiation of land plants led to a drastic increase in soil weathering, or soil development and weathering, and then an unprecedented nutrient flux into the Devonian oceans. And then this led to eutrophication, eventually leading to anoxia, and this widespread anoxia is what probably caused all of these marine mass extinctions. So this is a great theory. It has a few challenges, however. The first of which is that it's kind of a simplistic roots off, roots on approach. So we go from no roots to roots and a pulse of weathering. In reality, this probably happened in multiple smaller pulses at different times in different locations. And then phosphorus is cited as a primary driver of this eutrophication. But we don't have a constraint on how much phosphorus was exported and when. And this is primarily due to the challenges in interpreting marine records for phosphorus in particular. It's very difficult to get a handle on export from land using marine records. So we need kind of a new way to look at this. And we would argue that probably a really good way to do this is to look at lakes. Lakes offer a very unique high-resolution record of sediment input and nutrient input. So why not use these to try to get a handle on phosphorus transformations, and then kind of get this information from different points in the paleo Earth and put them together to try and create a global model and see, can we actually constrain the phosphorus release in time and amount? So obviously, there would have been tremendous transformations within lakes for other nutrients as well, including nitrogen and carbon. So we're going to look at that as well. But we essentially agree with Algeo in that this mobilization from phosphorus was caused by, or mobilization from land plants caused some phosphorus to dump into the oceans and eventually resulted in these biotic crises in the Devonian. So basically, the first couple steps that we took was to look at some sample sites in the Orcadian Basin. So the first of which was Sandside Bay in northern Scotland, and the second of which was Ella Island in Greenland. So these are pretty good sites because they are geographically separated. However, they share a common formation in that they're both formed in the vicinity of the Caledonian Mountains. So we've got some similarities, but we've also got enough separation to hopefully tell us a good story. So just to give you some kind of paleogeographic framework here, so the two sites labeled Greenland and then Orkney, Shetland, basically the same as our northern Scotland site. You can see that they're very close in the Paleo Earth. They're both located on Euramerica. A little more information on both of those sites. As I mentioned, formed under similar conditions, both extensional basins formed from the uplift of the Caledonian Mountains. They're temporally similar. The Scotland sites are from the late Iphilian, and the Greenland sites are from kind of the early to mid-Givettian. So they're very close together, geologically speaking. The Scotland site is significant because it's coincident with the appearance of the first Archaeopteryx trees. And the Greenland site also contains preserved stems of Svalbardia, which is basically a cousin of Archaeopteryx. So let's get into some of the results. Some of our initial results, which have been presented before from Scotland, basically show a fairly large phosphorus pulse, and you can see highlighted in the orange area, right around the time that we would expect to see the first Archaeopteryx trees. So this graph basically shows phosphorus normalized to some terrigenous elements to kind of weed out the effects of sediment focusing and things like that. But basically what we see is a large nutrient pulse coincident with the appearance of Archaeopteryx. So that's great. So can we reproduce that somewhere else? And the answer is yes, we can. So these are our results from Ella Island, Greenland. Basically the same analyses, so phosphorus as well as some terrigenous elements. And we see the exact same pulse of phosphorus across all these graphs here, highlighted in the gray. So again, we have a nutrient pulse similar to the pulse in Scotland. And so, is this a coincidence? And I would like to think that it's not a coincidence. We have two similar but geographically separated lakes. The nutrient pulses are similar in magnitude and nature. The timing is similar, and they're coincident with the appearance of the first trees. So, this is pretty exciting, but of course it doesn't tell a global tale. Because again, we're in Euramerica. We haven't looked at anything on Gondwana yet. So that's kind of the next step and what we're working on currently. So we've kind of focused our studies on the Iphilian, Givettian, lacustrine sequences or near lacustrine sequences to see if we can find some more of these results in other places, particularly Gondwana or Paleo-China. We're currently analyzing another sequence from the Greenland, which is a fluvial sequence, again from the Givettian. Hopefully going to give us some similar results. But ideally, we'd like to have samples from all over the Paleo Earth. We don't have any from Paleo-China at the moment. We don't have any from Russia, but we do have some from West Falklands, Bolivia, some more from Orkney, and possibly have access to some in New York and Pennsylvania. So there's potential to have a pretty good data set here. So just to kind of wrap everything up here, by looking at lakes, we think that we could possibly answer this long-standing scientific question and ultimately better understand the evolution of our own biosphere. And then obviously, in the spirit of the conference, if we can understand our own planet, that gives us a much greater chance of understanding other planets. So with that, if we have time for questions.
Yeah, I didn't quite understand the reasoning. You have plants develop roots, and then these roots, what do? They crack the rocks, and that makes this phosphorus pulse possible?
That's essentially it, yeah. So,
but that's weird. I would think that's weird because these roots are presumably phosphorus is a valuable thing to them. So why would they produce it for other things?
Yes. So they basically mobilize this phosphorus from the mineral apatite. And they don't use all of it, so what they don't use essentially gets washed through runoff.
Why would they mobilize something that they don't use?
Well, they do use it. They just don't use all of it. So that's kind of the key. So
Why don't they have fewer roots then?
It's a great question.
Sort of in that line, is there any, do you have any sort of a way to think about if you're talking more about, like, again, mobilization of stuff that never goes into the biomass, or you're suddenly making all this biomass and it starts rotting and all the stuff that it's rotting goes downstream and everything? Like, is there a way to try to tell if there's, if you're more talking about material that didn't wind up in life on the land, or stuff that, or sort of increase in land biomass that then washes away?
Yeah, no, that's a great question. Yeah, I don't really know how you could necessarily tease out the differences there.
Yeah.
But yeah, that's, I mean, that's
I'm not familiar with if there's isotopes or anything that, so, yeah.
Hi, I'm Bethany Teeling. So I also work on the Silurian and Devonian, which is great, so I was excited to see this talk. I was wondering if you guys had just, like, considered the fact that you're very close to this, I call it the Pangea, like early Pangean collisional zone, so you're very, very close, and all your samples are going to be very close to that. Are you concerned at all about the different kinds of fluxes that you might get being so close to these uplifts, and that you're necessarily going to get more weathering being closer to those uplifted areas?
Yeah, so that, I mean, that's definitely a consideration as well. So when we try to conduct other analyses and kind of normalize phosphorus to other elements, that's kind of we kind of try to eliminate sediment focusing if we can, but that is for sure a potential issue with respect to, like, also just how close these lakes are to the mountains, and potential, just things like, just rock slides, things like that, exposing fresh surfaces, exposing more apatite. So that's definitely consideration.
I have a very naive question. On your graph, towards the end, you also have a second phosphorus peak.
Yeah, okay, so...
Does that correspond to anything interesting?
So you're talking about this one down here?
Yeah.
Yeah, so I don't have any particular analysis on that particular peak, but yeah, for sure. I mean, you can see that is a definite signal. It's at the end of our data set, so that's kind of why I didn't really mention it, because we can't really say too much about it. But we have definitely some plans to go back and resample some of these, because these samples right here I did not collect. So these were actually collected by Dr. Marshall in Southampton. So we've kind of used his data set and then analyzed his samples. So he allowed me to subsample his catalog. But ideally, I would like to go back and I would like to get some more, a bigger slice in time.
Thank you.
Hi, Heather Graham, kind of on the same line of questioning, thinking mechanistically about where this phosphorus is coming from. Are there any good biomarkers, or have you looked for any organic evidence that might tell you a little bit about root exudates that help mobilize this material?
Yeah, so we haven't necessarily looked at root exudates particularly, but as far as biomarkers go, we're basically using pollen assemblages to tell us, like, what was present during the period. So we have, in the case of Scotland, we have, evidence of some of the early trees and whatnot. And in Greenland, we actually have stems from Svalbardia. So we're definitely looking at biomarkers. That is probably one of the weaker points of our study at the moment, and one of the criticisms on our NSF proposal. So yeah, we are for sure trying to...
So a cool thing that you might want to look at the bottom of this, where you're seeing that other peak, since you're doing palynology, is maybe think about looking at your fungal spores too, since that's going to have a lot of weathering effects as well.
Yeah. Thank you.
Hi, I'm Michael. Do you have a sense of what time is represented by your pulse there, and what the how long your lake may have persisted?
Yeah, and that's another weakness of our study is we do not have a very good constraint on these ages. So I can tell you that this is probably over the course of maybe a couple million years, and that's probably about as best as I can do. And hopefully we can constrain that a little bit better before if we can get this to publication.
So,
at
I
some
mean,
point.
millions of years, that's a pretty long-lived
Yeah,
lake.
yeah, for sure.
Let's thank Matthew Smart again.